Have you ever stood outside on a clear night, gazing up at the stars, and felt that overwhelming sense of wonder? The universe stretches out before us, an infinite tapestry of light and mystery, and in those quiet moments, it's impossible not to ask, just how far does it all go? What lies beyond the farthest galaxies we can see, and is there even an edge to it all? These questions aren't just the stuff of late-night stargazing. They've haunted humanity for thousands of years. From the earliest philosophers who mapped the heavens with naked eyes to the modern astrophysicists peering through colossal telescopes, we've been chasing the same elusive truth. What is the ultimate cosmic limit? This isn't just a question about distance or scale. It's about the very nature of existence. Think about it. If the universe has a boundary, what's on the other side? Empty space, another universe, or does the idea of an edge simply not make sense in the grand scheme of things? The answers we're uncovering today are more astonishing than anything our ancestors could have imagined. Some theories suggest the cosmos might be infinite, stretching forever without end. Others propose that our universe is just one bubble in an endless cosmic foam, with countless other realities floating beside us. And then there's the mind-bending possibility that the universe might be curved, looping back on itself like a vast cosmic Möbius strip. But why does this question even matter? Because the search for the universe's limits is really a search for our place within it. Every time we push the boundaries of what we know, we're not just exploring space, we're exploring ourselves. This journey will take us from the ancient thinkers who first dared to measure the heavens to the cutting-edge science that's rewriting our understanding of reality. Along the way, we'll confront paradoxes, wrestle with impossible scales, and maybe, just maybe, catch a glimpse of the ultimate truth hiding in the depths of the cosmos. So buckle up. The answers won't be easy, but the ride will be unforgettable. To grasp just how vast our cosmic neighborhood truly is, we first need to understand the idea of the observable universe. Picture a sphere around us, stretching 93 billion light-years in every direction. That's the portion of the cosmos we can potentially see. But here's the catch. This isn't just about distance. It's a window into the past. Because light takes time to travel, every star, galaxy, or quasar our wee spot is a snapshot of how it looked when that light began its journey, sometimes billions of years ago. The farther out we look, the closer we get to witnessing the universe in its infancy. But why is there a limit at all? It all comes down to the speed of light and the relentless expansion of space itself. Even though light moves astonishingly fast, about 671 million miles per hour, it still hasn't had enough time since the Big Bang to reach us from regions beyond that 93 billion light-year boundary. And as the universe stretches, those distant galaxies are being carried away from us even faster, their light forever lost in the expanding void. This is where tools like the Hubble Space Telescope become cosmic time machines. By collecting faint glimmers of light from galaxies near the edge of our observable bubble, Hubble has given us glimpses of the universe when it was just a fraction of its current age. Yet for all its power, Hubble, and even its successor, the James Webb Space Telescope, can't see beyond that horizon. It's like standing on a shoreline, watching waves roll in from distant storms we'll never fully witness. Which leads us to the tantalizing question, what lies beyond? If the observable universe is like a campfire's glow in an endless forest, how much darker does the woods get? Current theories suggest the full universe could be hundreds of times larger than what we see, or even infinite. Some regions might be forever hidden, their light outpaced by the stretching fabric of space. Others could harbor entirely different configurations of matter, physical laws, or even other cosmic bubbles like our own. The observable edge isn't a wall, it's just the limit of our vision, a horizon beckoning us to wonder what's really out there. That shimmering edge of the observable universe, the cosmic horizon, isn't just a distant line in the sand. It's more like standing on a beach at night, watching the last flicker of a ship's lantern vanish as it sails beyond the curve of the Earth. Beyond that point, the light simply hasn't had enough time to reach us, no matter how powerful our telescopes become. But here's where things get truly fascinating. The universe doesn't stop there. Inflation theory, one of the most groundbreaking ideas in modern cosmology, suggests that what we can see is just a speck in a reality so vast, it defies human intuition. Imagine blowing up a balloon with tiny dots scattered across its surface. As the balloon expands, the dots move farther apart, just like galaxies drifting in our expanding universe. Now picture this, the balloon is so enormous that even as it inflates, most of its surface remains hidden from any single dot's perspective. That's our cosmic horizon, and not a true edge, but a limit to how much of the balloon's surface we can glimpse from our tiny vantage point. According to inflation, the universe underwent a mind-boggling growth spurt in its first fraction of a second, stretching far beyond what we'll ever observe. Some estimates suggest the full universe could be at least 10 to the power of 23 times larger than the observable portion. That's a 1 followed by 23 zeros, a number so colossal, it makes the grains of sand on every beach seem insignificant. So what does this mean for the idea of a cosmic limit? It's like trying to map an endless ocean by studying a single wave. The horizon we see isn't a wall, it's a curtain, and behind it could be anything more: galaxies, exotic structures, or even regions where the laws of physics play by entirely different rules. Some theories propose that inflation never truly stopped, meaning countless other universes might be bubbling into existence beyond our horizon, each with its own unique properties. This realization transforms the cosmic horizon from a boundary into a doorway, one we can't walk through, but one that invites us to rethink what limit even means in an ever-expanding reality. The universe isn't hiding its size from us. It's just too grand, too dynamic for light to carry all its secrets across the void. And that's the most humbling part. The more we learn about the horizon, the more we understand how much lies forever beyond our view. But to truly grasp how the universe could be so unimaginably vast, we need to dive into one of the most revolutionary ideas in cosmology: inflation theory. Picture the universe in its first moments, not even a trillionth of a second old. Instead of a slow, steady expansion, space itself underwent an exponential growth spurt, doubling in size over and over again faster than the blink of an eye. This wasn't just expansion, it was hyperdrive. In that fleeting instant, a speck smaller than an atom could have stretched to scales far beyond our entire observable universe today. This explains why the cosmos appears so uniform in every direction we look. Distant regions that should never have had time to interact, regions now billions of light years apart, share nearly identical temperatures and properties. Inflation smoothed everything out in that explosive stretch, like pulling on a wrinkled sheet until every crease vanishes. But here's the mind-bending part. If inflation could stretch our observable universe from a microscopic speck to 93 billion light-years across, why would it stop there? The math suggests it didn't. Most of the universe likely kept expanding far beyond what we'll ever see, like a loaf of raisin bread where our observable cosmos is just one tiny raisin in an endless bakery. And that's where things get even wilder. If space kept inflating beyond our horizon, it might have created not just more universe but other universes entirely. This is the multiverse hypothesis. Imagine a cosmic bubble bath, where each bubble is its own self-contained universe with its own physics, its own constants, even its own version of time. In some, gravity might be stronger. In others, matter might behave in ways we can't fathom. Our universe's rules, the speed of light, the strength of gravity, could be just one random configuration in an infinite cosmic lottery. So when we ask about the ultimate cosmic limit, we might be asking the wrong question. There may not be a single edge to the universe, just countless horizons, each marking the boundary of a different cosmic bubble. Some could be similar to ours, with galaxies, stars, and maybe even life. Others might be barren or so alien that the very concept of a limit wouldn't apply. And if the multiverse is real, then our cosmic horizon isn't the final frontier, it's just the edge of our neighborhood in a reality too vast for any one universe to contain. This raises a humbling possibility. What we call the limit of our universe might be nothing more than a quirk of perspective. Like a sailor in the age of exploration, convinced the ocean ends at the horizon, we might be mistaking the edge of our vision for the edge of existence. The true cosmic limit, if there is one, could lie far beyond our reach, hidden behind layers of inflation, multiverses, and dimensions we're only beginning to theorize. And that's the beauty of it. The universe keeps its deepest secrets just out of sight, inviting us to keep searching, keep questioning, and keep wondering what lies beyond the next horizon. The shape of the universe isn't just a question for philosophers, it's a puzzle written in the very fabric of space itself, and the answer could redefine everything we know about cosmic limits. Think about it like this: if you could step outside the universe and look back, would it stretch endlessly in all directions like an infinite sheet of paper? Or would it curve gently, wrapping around itself like the surface of a giant balloon? Or maybe, just maybe, it bends in ways so strange they defy everyday intuition. These aren't just abstract ideas, they're real possibilities scientists are testing right now. And the geometry of the cosmos holds the key to whether the universe is infinite, finite, or something even more extraordinary. Take a flat universe, for example. If space has no curvature, like a perfectly level tabletop, parallel lines would never meet, and the cosmos could stretch on forever without boundary. This is the simplest scenario, and oddly enough, it's what our best measurements suggest. Missions like NASA's Wilkinson Microwave Anisotropy Probe and the Planck spacecraft have spent years studying the cosmic microwave background, the faint afterglow of the Big Bang. By mapping its tiny temperature fluctuations, they've found space appears astonishingly flat, with any curvature too subtle to detect. But here's the catch: a flat universe doesn't have to be infinite. It could also fold back on itself in hidden dimensions, like a video game world where stepping off one edge teleports you to the opposite side. Imagine flying a spaceship straight ahead for long enough. Could you end up right back where you started? In a closed universe with positive curvature, that might just be possible. Now picture the opposite, an open universe where space curves outward like a saddle. In this scenario, parallel lines would diverge forever, and the cosmos would stretch without end, expanding faster and faster into eternity. No loops, no boundaries, just an endless, accelerating sprawl. While this might sound like science fiction, it's a real mathematical possibility, and it raises a haunting question. If the universe is open, does size even have meaning when there's no edge to measure? But the most intriguing part isn't just the shape itself. It's what these geometries imply about the universe's fate. A closed universe might eventually stop expanding and collapse in a big crunch. while an open or flat one could keep stretching until every galaxy vanishes over the horizon. And then there's the wild card. What if the universe isn't just one shape? Some theories suggest it could be patchwork, with regions of different curvature stitched together like a cosmic quilt. So when we talk about the ultimate cosmic limit, we're really asking how space itself is woven. The answer might be hiding in those ancient photons from the cosmic microwave background, or in the way distant galaxies bend light around them. Or perhaps, like so much of cosmology, it's waiting just beyond the edge of our understanding, teasing us with glimpses of a truth we're only beginning to grasp. Dark energy is the universe's greatest unsolved mystery, a force so strange it makes the cosmos behave in ways that defy common sense. Picture this: every galaxy, every star, every speck of dust in space isn't just drifting apart, it's being pushed outward faster and faster, as if some invisible hand is stretching the fabric of reality itself. Back in the late 1990s, astronomers made a discovery that turned cosmology upside down. They expected the universe's expansion to slow down over time, pulled by gravity's relentless tug. Instead, they found the opposite. The cosmos wasn't just expanding, it was accelerating, as if some unseen energy were pouring fuel on the cosmic fire. They called it dark energy, and to this day, we still don't fully understand what it is. This isn't just a curiosity, it's a ticking clock for the universe's fate. If dark energy keeps strengthening, it could lead to scenarios straight out of science fiction. Take the Big Rip, a theory physicist Brian Greene describes as the universe's most dramatic possible end. Imagine dark energy growing so powerful over billions of years that it doesn't just push galaxies apart, it tears them apart. Stars, planets, even atoms themselves could be ripped to shreds as space stretches faster than the forces holding matter together. It's a chilling thought, but it's not the only possibility. Some models suggest dark energy might weaken over time, allowing the universe to expand forever at a gentler pace. Others propose it could fluctuate, leading to cycles of acceleration and collapse. What makes dark energy so baffling is that it seems to be woven into space itself. Unlike matter or radiation, it doesn't dilute as the universe grows, its density stays constant, meaning its influence becomes more dominant as everything else spreads thinner. Think of it like adding more stretch to a rubber band the longer you pull. This could mean that in the far future, dark energy will dominate so completely that distant galaxies will vanish from view, their light stretched beyond detection. The cosmos will become a vast, empty expanse, with isolated islands of stars drifting further and further into darkness. Yet for all its mystery, dark energy might hold the key to understanding the universe's ultimate limits. Is there an edge to space, or does it go on forever? Could dark energy's push eventually overcome gravity's pull, unraveling the very structures that hold reality together? Or will it simply fade into the background, leaving the cosmos to expand quietly into eternity? The answers aren't just hidden in equations, they're written in the distant light of supernova, in the subtle warping of space-time, and in the echoes of the Big Bang itself. One thing's certain: dark energy isn't just shaping the universe's fate, it's rewriting the story of everything we thought we knew. The universe's fate hinges on a cosmic tug of war between two opposing forces: gravity's relentless pull and dark energy's mysterious push. Depending on which wins, our cosmos could meet one of two starkly different endings, each rewriting what we mean by limits. First, picture the Big Crunch, a dramatic finale where expansion reverses into collapse. Imagine all galaxies like embers flung from an explosion, slowing their flight and falling back inward. Space itself contracts, temperatures soar, and eventually everything condenses back into a singularity, a mirror image of the Big Bang. It's the ultimate cosmic boomerang where the universe's limit isn't an edge in space, but an endpoint in time. Stars in this scenario would share the fate of massive suns that exhaust their fuel, collapsing under their own weight, just on a scale so vast it bends the mind. Now contrast that with heat death, a slow fade into darkness. Here, expansion never stops. Galaxies drift further apart until their light can no longer bridge the void. Stars burn out, black holes evaporate, and space becomes a vast, near-empty graveyard where even time loses meaning. This isn't a violent end, it's exhaustion, like a campfire reduced to cold ash. The universe's limit here isn't a boundary, but a state, maximum entropy, where energy is so evenly spread, nothing can change anymore. Think of it like a balloon stretched so thin, its surface goes utterly still. What's fascinating is how these opposing fates redefine the idea of boundaries. The Big Crunch suggests a finite universe with a literal expiration date, while heat death implies an infinite, lifeless expanse. Both challenge our intuition about endings. After all, how do you visualize a limit when the universe either vanishes into a point or dissolves into endless cold? Yet there's a deeper twist. These scenarios aren't just about far future doom. They're clues about the universe's shape today. A Big Crunch favors a closed, curved cosmos where gravity ultimately triumphs, while heat death aligns with a flat or open universe where dark energy dominates. So when astronomers measure the cosmic microwave background or track supernova, they're not just mapping the past, they're reading the universe's last chapter in advance. And that's the ultimate irony. The cosmos might have no spatial edge, yet it could still be bounded by time. Whether it collapses or freezes, the real limit isn't where space ends, it's when the story does. Quantum mechanics shatters our everyday notions of reality, revealing a universe that's anything but static. At the smallest scales, empty space isn't empty at all. It's a seething, bubbling cauldron of activity. Particles and their antiparticles flicker into existence for fleeting moments, borrowing energy from the vacuum before annihilating each other, like cosmic fireflies blinking in the dark. These quantum fluctuations aren't just theoretical quirks. They've been measured in labs, proving that what we call nothing is actually teeming with potential. Now here's where it gets truly wild. Some theories suggest these tiny fluctuations could be the seeds of entire universes. Picture a quantum bubble forming in the vacuum, a speck of spacetime that, under the right conditions, inflates explosively, birthing a cosmos separate from our own. Stephen Hawking explored this mind-bending possibility in his work on quantum cosmology, proposing that the universe might not need a singular, definitive beginning. Instead, it could emerge from a quantum event like a ripple in an endless ocean of possibilities. This idea turns the concept of cosmic limits upside down. If new universes can sprout from quantum foam, then the edge of our universe might not be a boundary at all. It could be a doorway to an infinite multiverse, each with its own laws, its own history, even its own version of time. Some of these baby universes might collapse instantly, while others could expand into vast, complex realms like ours. It's as if reality is a cosmic kaleidoscope, constantly rearranging itself into new patterns. But how could something as ephemeral as a quantum fluctuation create a whole universe? The key lies in inflation, the same explosive expansion thought to have shaped our early cosmos. If a quantum bubble catches the right wave of inflationary energy, it could balloon into a self-contained reality, completely detached from its parent universe. Think of it like blowing soap bubbles. Some pop immediately, while others drift away, becoming their own shimmering worlds. Hawking's vision challenges us to rethink not just the universe's size, but its very nature. What if the Big Bang wasn't a one-time event, but part of an endless cycle of creation? What if every quantum flicker holds the potential for a new cosmos, resetting the idea of limits entirely? The answer might lie in the fabric of spacetime itself, where the lines between here and elsewhere blur into quantum uncertainty. This isn't just speculation, it's a frontier. Experiments probing the cosmic microwave background or the behavior of black holes could one day reveal traces of these sibling universes, hidden like echoes in the static of our own. Until then, the quantum vacuum remains the ultimate cosmic wildcard, whispering that the universe's greatest limit might just be our imagination. Black holes aren't just cosmic vacuum cleaners, they might be the universe's most extreme shortcuts. Picture a singularity, a point where gravity becomes so intense that not even light can escape. But what happens to all that matter and energy pulled into the abyss? Some theories suggest it doesn't just vanish, it could emerge somewhere else entirely, like water spiraling down a drain only to bubble up in another pool. This is where the idea of wormholes comes in. Imagine folding a sheet of paper so two distant points touch. A wormhole would be the tunnel piercing through that fold, connecting regions of spacetime that should be impossibly far apart. Einstein's equations actually allow for such bridges, though they'd require exotic matter to stay open. Now, consider white holes, the hypothetical opposite of black holes. If a black hole is a one-way door where everything enters and nothing leaves, a white hole would be an exit, spewing out matter and energy like a cosmic fountain. Some models suggest that every black hole could be linked to a white hole in a distant part of the universe, or even in another universe altogether. It's as if the cosmos has built-in emergency exits, hidden in the most violent places imaginable. But here's the catch: traversing a black hole isn't exactly a leisurely cruise. The tidal forces near the singularity would stretch any object into spaghetti long before it could reach the other side. Even if a wormhole existed, surviving the journey would require physics we don't yet understand. Yet the mere possibility rewrites what we mean by limits. If black holes can connect disparate regions of spacetime, then the universe's boundaries aren't just physical distances. They're threads in a vast, knotted tapestry, with hidden pathways woven into the fabric of reality itself. This isn't just science fiction. The math behind wormholes and white holes emerges from the same equations that describe black holes. The difference is scale. While black holes are observed daily, their hypothetical counterparts remain elusive. But their potential existence hints at something profound. The universe might not have edges in the traditional sense. Instead, it could be a labyrinth of interconnected portals, where the shortest distance between 2 points isn't a straight line, but a plunge into the unknown. So what does this mean for our search for cosmic limits? It suggests that boundaries might be illusions shaped by our limited perspective. A black hole's event horizon looks like a barrier from the outside, but for a hypothetical traveler, it could be a gateway. The universe's true architecture might not be about walls and edges, but about folds, tunnels, and bridges waiting just beyond the reach of our telescopes, challenging us to rethink what beyond even means. String theory rewrites the cosmic rulebook by proposing that the universe isn't just three-dimensional. It's a symphony of hidden dimensions vibrating beneath the surface of reality. Imagine space as a bedsheet stretched tight. To an ant crawling across it, the sheet seems flat, two-dimensional, but you, standing above, see the folds and wrinkles the ant can't perceive. That's the essence of higher dimensions. String theory suggests there could be 11 dimensions, total 10 of space, one of time curled up so tiny they're invisible to our everyday experience. These extra dimensions aren't just empty space. They're the stage where the smallest particles dance, their vibrations determining everything from gravity to the mass of an electron. Now picture our universe as a slice of bread floating in a cosmic loaf. In this analogy, the loaf is the bulk, a higher dimensional space, and our universe is a three-dimensional brain, short for membrane, embedded within it. Other brains might float nearby, each hosting its own universe with different physical laws. Gravity, unlike other forces, could leak between brains, which might explain why it's so weak compared to electromagnetism or the nuclear forces. This brain world scenario turns the cosmic limit from a boundary into a layer, one of many stacked realities, separated by dimensions we can't see but might someday detect. The math behind this is staggeringly elegant. Just as a violin string can vibrate at different frequencies to produce distinct musical notes, tiny strings in these higher dimensions vibrate to create particles. An up quark, a photon, even the Higgs boson, they're all the same fundamental string, just humming different tunes. This harmony could unify all forces of nature, solving puzzles like why gravity and quantum mechanics refuse to play nice in our current models. But here's the catch: these extra dimensions aren't just small. They could be warped, shaping reality in ways that make some corners of the universe fundamentally unreachable. Think of it like a mountain range where some valleys are hidden behind impassable ridges. If a dimension were folded into a Calabi-Yau shape, a complex, six-dimensional geometric form, it could create valleys in particle behavior we've yet to map. This might explain why we haven't found signs of these dimensions yet. Our particle colliders simply lack the energy to climb those cosmic ridges. But future experiments, like those searching for microscopic black holes or gravitational anomalies, might uncover traces of these hidden landscapes. So where does this leave the idea of cosmic limits? If higher dimensions exist, the universe isn't just vast, it's multi-layered, with realms existing literally millimeters away from us in dimensions we can't perceive. A boundary might not be a place you could travel to, but a direction you can't point in. It's as if we've spent centuries studying shadows on a cave wall, unaware the real action is happening in the space above our heads. String theory doesn't just expand the universe, it redefines what expansion even means, suggesting that the ultimate cosmic limit might not be a wall at the edge of space, but the edge of our perception itself. What if everything we see, the stars, galaxies, even the space between them, is just a grand illusion? That's the jaw-dropping premise of the holographic principle, a theory so radical it turns our understanding of reality inside out. Imagine a universe where the three-dimensional world we experience is nothing more than a projection, like a movie playing on a cosmic screen. But here's the twist: the screen isn't some futuristic device, it's the universe's outer boundary, a two-dimensional surface where all the information about our 3D reality is encoded. Think of it like a hologram on a credit card. Tilt it, and the flat surface creates the illusion of depth. According to physicists like Leonard Susskind, the entire cosmos might work the same way, with every particle, every force, even time itself, emerging from information etched on a distant, two-dimensional edge. This isn't just philosophical musing, it's math with real consequences. Black holes played a pivotal role in sparking this idea. When matter falls into a black hole, what happens to all the information it carries? Quantum mechanics says information can't be destroyed, but general relativity suggests it vanishes forever. The holographic principle offers a wild solution: the information isn't lost. Instead, it's smeared across the black hole's event horizon, the point of no return, like a cosmic hard drive recording everything that falls in. Scale this up, and the entire universe could be a vast, interconnected hologram, with the 3D world we perceive merely a shadow of the real action happening at the edges. But how does this redefine something as basic as size? If the universe's true workings are two-dimensional, then volume. the very thing that makes space feel vast, might be an emergent property, not a fundamental one. It's like realizing the characters in a video game aren't actually inside your screen. They're just patterns of pixels creating the illusion of depth. Suddenly, the universe's scale becomes a kind of cosmic sleight of hand, where distances and dimensions are secondary to the information that generates them. This leads us to an even deeper revelation. Information might be the universe's true currency. Forget matter or energy. The bits and bytes of cosmic data could be the bedrock of reality. Modern cosmology is increasingly embracing this idea, from the way black holes store information to theories that spacetime itself is woven from quantum entanglement, a kind of subatomic networking that links distant particles instantaneously. If the holographic principle holds, then the universe isn't just expanding, it's computing, processing information at scales we're only beginning to fathom. And that changes everything. The search for cosmic limits isn't about finding walls or edges. It's about decoding the cosmic algorithm that makes reality seem real in the first place. So the next time you look up at the night sky, consider this. The vastness above you might be the ultimate illusion, a 3D movie projected from a hidden, two-dimensional script. The universe's true boundaries aren't in the stars, they're in the information that paints them into existence. And if that's the case, then the ultimate cosmic limit isn't a place at all. It's the point where reality runs out of bits to tell its own story. If black holes are the universe's ultimate shredders, then entropy is the cosmic tax collector, slowly eroding order into chaos, one particle at a time. But here's the paradox. While entropy demands that information can never truly vanish, black holes seem to defy this rule, swallowing stars, planets, and light without a trace. This contradiction sent shockwaves through physics when Stephen Hawking proposed that black holes don't just consume matter, they evaporate over eons, leaking energy now known as Hawking radiation. The catch: his original math suggested the radiation carried no information about what fell in, implying the universe's ledger could have permanent gaps. Cue decades of debate. If information is truly lost, it would rewrite quantum mechanics itself. Enter the holographic principle, which offers a stunning solution. Imagine a black hole's event horizon as a scrambled hard drive. As matter crosses it, its information isn't destroyed, it's smeared across the surface in quantum bits so fine, they're effectively a two-dimensional backup. Hawking later conceded this might be possible, but the implications ripple far beyond black holes. If even the densest objects in existence can't erase data, then the universe might operate like an indestructible archive where every interaction, from a supernova to a falling leaf, is permanently logged. This raises a profound question. Could entropy and information preservation actually define the universe's limits? Think of entropy as cosmic sprawl. The more the universe expands, the more disorder grows, and the harder it becomes to store or retrieve information. Distant galaxies receding beyond our horizon aren't just vanishing. Their data is becoming irretrievable, like books locked in a vault with no key. Some theories suggest this could set a soft boundary to reality. Not a physical edge, but a point where the universe's hard drive runs out of readable sectors. Yet there's a twist. If information is truly conserved, then the cosmos might have a built-in compression algorithm. Just as a zip file condenses data without loss, the holographic principle implies our three-dimensional reality could be a projected illusion, with all its complexity encoded on a distant two-dimensional boundary. In this view, the universe's limit isn't about space, it's about bandwidth. How much information can fit on that ultimate cosmic hard drive, and what happens when it's full? The answer might lie in the dance between entropy and quantum mechanics. While entropy pushes toward disorder, quantum entanglement, the ghostly link between particles across vast distances, could weave a hidden order into the chaos. Black holes might be the testing ground. As they evaporate, their information could re-emerge in Hawking radiation, like a burned document reconstructed from its ashes. If so, the universe's true limit isn't a wall or an endpoint, but a cosmic balance between forgetting and remembering, where every bit of data, from the birth of a star to the blink of an eye, is etched into the fabric of reality itself. So when we ask how big the universe can get, we might really be asking, how much can it know? The answer could rewrite not just cosmology, but the very meaning of existence. After all, if information is the universe's currency, then its ultimate limit might be measured not in light years, but in bits. The staggering scale of the cosmos doesn't just challenge our understanding of space, it throws one of humanity's biggest questions into sharp relief. If the universe is so vast, why does it feel so empty? This is the essence of the Fermi Paradox, the unsettling gap between the high probability of alien civilizations and the total lack of evidence for them. And when we start connecting it to the idea of cosmic limits, things get even more intriguing. Picture a universe so enormous that even if life were everywhere, the distances between civilizations could be unimaginably vast. The nearest intelligent neighbors might be millions of light years away, their signals fading into noise long before they reach us. In a cosmos without boundaries, isolation might be the ultimate rule. But distance isn't the only barrier. Time itself could be working against us. Civilizations might rise and fall in the blink of a cosmic eye, their existence separated by eons. Imagine two societies blossoming in different galaxies, one while dinosaurs still roamed Earth, the other long after our sun has burned out. Even in an infinite universe, the odds of overlapping lifetimes could be vanishingly small. And if dark energy keeps accelerating expansion, the window for contact might be closing. Galaxies already racing beyond our horizon could carry potential neighbors away forever, their light stretched into oblivion before we ever detect them. Then there's the darker possibility. What if civilizations hit a ceiling, a great filter, as some call it, a catastrophic challenge so inevitable, no society survives it? This could be anything from self-destructive technology to cosmic disasters we haven't yet imagined. If the universe is infinite but lifeless, the real limit might not be space, it could be time. The silence we hear when listening for alien signals wouldn't be emptiness, but a graveyard of civilizations that never made it far enough to bridge the void. Yet there's another angle. What if we're not alone but simply uninteresting? Advanced societies might regard the universe so differently that communication becomes pointless. To a civilization harnessing black holes for energy or navigating higher dimensions, radio signals might seem as primitive as smoke signals, or perhaps they've moved beyond physical forms entirely, existing as pure information in some quantum substrate we can't perceive. The universe's true inhabitants could be all around us, hidden in plain sight by the limits of our own perception. So when we ask about cosmic limits, we're really asking about connection. An infinite universe doesn't guarantee company. It might ensure the opposite, scattering intelligence so thinly that each civilization becomes an island. The Fermi Paradox isn't just about aliens, it's a mirror forcing us to confront how fragile and fleeting our place in the cosmos might be, and that changes the question entirely. Instead of wondering where everyone is, we should ask, in a universe this vast, how do we make sure we're not the ones who disappear without a trace? The cosmic microwave background isn't just static on an old TV. It's the oldest light in the universe, a fossilized whisper from the moment the cosmos became transparent. Picture this: 380,000 years after the Big Bang, the universe cooled enough for atoms to form, releasing a burst of radiation that's been traveling ever since. Today, that glow has stretched into faint microwaves, bathing the entire sky in a nearly uniform haze. But look closer, and you'll spot tiny fluctuations, hotter and cooler patches no larger than 100,000th of a degree. These aren't random noise, they're cosmic fingerprints, imprinted by quantum fluctuations in the universe's fiery infancy. Think of the CMB as a snapshot of the universe's toddler phase. Those subtle temperature variations, they're the seeds of everything we see today. Slightly denser regions pulled in more matter through gravity, eventually growing into galaxies and galaxy clusters. The pattern is so precise, it's like finding the blueprint for New York City in the brushstrokes of a cave painting. Missions like Planck and WMAP have mapped these fluctuations with stunning detail, revealing a universe that's flat to within a razor-thin margin, meaning space could stretch on forever, or at least far beyond what we'll ever observe. But here's where it gets even wilder. The CMB doesn't just tell us about the universe's shape, it hints at something stranger. One side of the sky shows slightly larger temperature variations than the other, a lopsidedness that shouldn't exist if the cosmos were perfectly uniform. Some theorists speculate this could be evidence of a pre-Big Bang era, or even that our universe collided with another bubble universe in the multiverse. Others suggest it's just a statistical fluke, a cosmic mirage we're misreading. Future telescopes like the proposed LightBird or CMB-S4 aim to settle these mysteries. With sensitivity sharp enough to detect primordial gravitational waves, ripples from inflation's explosive growth, they could uncover whether the universe underwent other phases before the Big Bang we know. It's like tuning a radio to a frequency no one's heard before, hoping to catch echoes of events we've only theorized. So when you hear that faint hiss of microwave static, remember, it's not just noise. It's the universe's first cry, carrying secrets about its birth, its size, and perhaps even its siblings in a reality far larger than we've dared to dream. Gravitational waves aren't just ripples in space, they're cosmic telegrams, carrying secrets from the farthest reaches of the universe. When LIGO first detected these faint tremors in 2015, it wasn't just a triumph of engineering, it was like giving humanity a new set of ears. Suddenly, we could hear collisions so violent, they warped the fabric of spacetime itself, black holes spiraling into each other, neutron stars smashing together in bursts of gold and radiation. But here's the real kicker. These waves might be our best shot at mapping the universe's hidden layers, including dimensions we can't even see. Take neutron star mergers, for example. When two of these ultra-dense stellar corpses collide, they don't just send out gravitational waves, they also unleash a fireworks show of light, gamma rays, and heavy elements. By comparing the gravitational signal with traditional telescope observations, scientists can test whether these waves behave exactly as Einstein predicted. Any tiny discrepancy, like the waves arriving slightly weaker or distorted, could hint at something mind-blowing, extra dimensions siphoning off energy, like echoes escaping into a hidden room. It's as if the universe has been whispering clues in a language we're only now learning to decode. The beauty of gravitational waves is their purity. Unlike light, which gets scattered or absorbed by cosmic dust, these ripples pass through nearly everything undisturbed. That means they carry information from places light can't reach, like the heart of a black hole merger or the edge of a collapsing supernova. Some theorists even suggest that advanced civilizations, if they exist, might use gravitational waves for communication, bypassing the limitations of electromagnetic signals entirely. But the real frontier lies in the subtle details. If hidden dimensions exist, they could leave fingerprints on gravitational waves, perhaps by altering how the waves weaken over distance or how they vibrate at different frequencies. Future detectors like the space-based LISA mission or next-gen ground observatories could catch these anomalies with precision unimaginable just a decade ago. We might discover that space-time isn't the smooth, four-dimensional canvas we thought, but a tangled web of higher dimensions, each leaving its mark on the waves that pass through. So when we talk about the universe's limits, gravitational waves offer more than just a new way to measure distance. They're a key to unlocking realities beyond our perception. The next time two black holes collide in the darkness, their ripples might carry more than just energy. They could be delivering a message from the edges of existence itself, written in the language of warped spacetime. And we're finally starting to listen. Neutrinos are the universe's ultimate ghosts, trillions of them streaming through your body every second, leaving no trace. These nearly massless particles are so elusive, they can pass through an entire planet like it's not even there. Born in the hearts of stars, supernova, and even the Big Bang itself, they carry whispers from the most violent events in the cosmos, untouched by the magnetic fields and dust that distort light. But their very invisibility makes them perfect cosmic messengers. If light is like a postcard that gets torn and faded on its journey, neutrinos are bulletproof envelopes, sealing their secrets until they're caught. That's where experiments like the Ice Cube Observatory come in. Buried deep in the Antarctic ice, this sprawling detector isn't hunting for light, it's waiting for the rare moment a neutrino crashes into an atom, producing a faint blue flash called Cherenkov radiation. It's like listening for raindrops in a thunderstorm. Most neutrinos slip through unnoticed, but the rare high-energy ones, those hurled across the universe by black holes or colliding galaxies, leave a trail bright enough to follow. In 2013, Ice Cube bagged its first big catch, neutrinos with energies millions of times greater than those from our Sun, their origin still a mystery. Some might have traveled from active galactic nuclei, where supermassive black holes spew jets of particles at near light speed. Others could be relics from the birth of the cosmos itself. But why do these ghostly particles matter in the search for cosmic limits? Because neutrinos don't just ignore matter, they ignore boundaries. A neutrino from beyond our observable universe could barrel straight through the cosmic horizon, carrying data from regions whose light will never reach us. Imagine a civilization on the other side of that horizon sending neutrinos like cosmic Morse code, bypassing the speed of light's tyranny. It's a long shot, but not impossible. Neutrinos might even hold clues to dimensions beyond our own. If extra dimensions exist, they could subtly alter how neutrinos oscillate between their three known types, electron, muon, and tau, leaving fingerprints in the data. The hunt for these phantom particles is just beginning. Upgraded detectors like Ice Cube Gen 2 and the proposed Pacific Ocean Neutrino Array aim to catch even fainter signals, building a map of the universe not in light, but in the silent traffic of neutrinos. Every time one is spotted, it's like intercepting a letter from a place we can't see, written in a language we're still learning to read. And in those cryptic notes, we might just find the answer to the universe's greatest riddle. How far does it all really go? What if everything we think we know about the universe, its vastness, its laws, even its very existence, is nothing more than lines of code in an unfathomably advanced simulation? This is the simulation hypothesis, a theory that blurs the line between science and philosophy, suggesting our reality might be an artificial construct. Elon Musk famously quipped that the odds we're living in base reality are 1 in billions, while philosopher Nick Bostrom laid the mathematical groundwork, arguing that if civilizations ever reach the capability to run ancestor simulations, the number of simulated minds would vastly outnumber real ones. Suddenly, cosmic limits take on a chilling new meaning. They're not physical barriers, but programming constraints. Picture a video game where the developer only renders the parts of the world the player can see. Beyond that boundary, nothing exists until it's needed. Now scale that up to the universe, the speed of light, a processing limit to prevent overload. Quantum indeterminacy, a way to save computational resources by not calculating particle states until observed. Even the mysterious dark energy driving cosmic acceleration could be a background program, tweaking the simulation's expansion rate. The eerie precision of the universe's physical constants just right for life to emerge might not be luck but intentional design. Bostrom's trilemma presents three stark possibilities. Either civilizations never reach post-human status, they choose not to run ancestor simulations, or we're almost certainly living in one. The first option seems unlikely given humanity's trajectory. The second assumes a universal taboo against simulation, which feels naive. That leaves the third, a statistical likelihood that we're digital beings in someone else's experiment. But here's where it gets truly bizarre. If we are in a simulation, the cosmic horizon might not be a fundamental limit of space, but a firewall where the simulation stops rendering. The quantum foam at the smallest scales, pixelation at the lowest level of resolution, and black holes could be data sinks, their singularities acting like cosmic recycle bins where information gets compressed or deleted. The simulation hypothesis doesn't just challenge our place in the universe, it redefines what the universe even is. Those distant galaxies we observe might not be physical objects, but procedural generation, like the repeating textures in a game engine. The Big Bang, a boot-up sequence. This perspective turns cosmology into a kind of reverse engineering, where physicists aren't uncovering nature's laws, but decoding the source code of reality itself. Yet for all its provocative appeal, the theory has its skeptics. Some argue it's unfalsifiable, a modern-day Cartesian demon with no way to test its claims. Others point out that even if we're in a simulation, the real universe would need its own physics to host the simulation, kicking the can down the road. But recent proposals, like looking for computational glitches in high-energy physics or anomalies in cosmic ray distributions, suggest we might one day find evidence. Whether metaphor or reality, the simulation hypothesis forces us to confront a profound question. If cosmic limits are just parameters in a program, who or what is the programmer? And more unsettling still, are we merely characters in their story, or could we someday hack the system from within? The answer might lie not in telescopes, but in the very fabric of reality, waiting to be decrypted. Time might be the most deceptive limit of all. We obsess over the vastness of space, the billions of galaxies, the unfathomable distances, but what if the real boundary isn't out there, but ahead of us? Or behind us, or even looping around us? Think about this. The universe has been around for roughly 13.8 billion years, but eternity stretches infinitely in both directions. If time truly has no end, then all possible events must happen, not just once, but an infinite number of times. This is the eerie premise behind Boltzmann brains, a thought experiment that twists our understanding of reality. Imagine a universe where random fluctuations in a sea of chaos spontaneously form fully conscious minds, complete with false memories of a past that never existed. According to some interpretations of thermodynamics, given enough time, these self-aware aberrations become inevitable. In the grand cosmic lottery, you're more likely to be one of these fleeting illusions than an actual, continuous consciousness anchored in a stable timeline. But time might not even play by linear rules. Some theories suggest the universe could be cyclical, collapsing and rebounding in an endless loop, a cosmic heartbeat where every Big Bang is just the aftershock of a previous big crunch. In this scenario, time isn't a straight line. It's a circle with every galaxy, every star, every version of you destined to repeat, slightly different each cycle. The equations of general relativity even allow for closed time-like curves paths where you could travel in time and end up right back where you started, like a cosmic Möbius strip of cause and effect. Then there's the more unsettling possibility that time itself could end, not with a bang but a whimper. In the heat-death scenario, the universe expands forever. Energy becomes too diffuse to sustain motion or thought, and time loses all meaning. Without change, without events, does time even exist? It's like asking whether a clock counts seconds if no one's left to hear it tick. The paradox is staggering. The universe might not have a spatial edge, but it could have a temporal one, a moment when the cosmic story simply stops mid-sentence. So is eternity the final frontier? If the universe is infinite in time, then every limit we perceive, the speed of light, the observable horizon, might just be temporary roadblocks in an endless journey. But if time is finite or cyclical, then the ultimate boundary isn't a place. It's an expiration date, and that changes everything. Instead of asking how far the universe extends, we should be asking how long it lasts and what happens when the clock runs out. Between the glowing filaments of galaxies and superclusters, the universe holds vast deserts of emptiness, cosmic voids so immense they defy comprehension. Picture the Laniakea supercluster, our galactic neighborhood, a sprawling web of 100,000 galaxies stretching over 500 million light-years. Now imagine the spaces between those threads, gaping chasms of nothingness where a single void can span hundreds of millions of light-years, containing fewer galaxies than a typical supercluster has in just one of its tendrils. These aren't just empty rooms in the cosmic house. They're missing floors, entire wings erased from the blueprint. The Boötes Void is one of the most famous, a spherical abyss nicknamed the Great Nothing, where astronomers expected to find thousands of galaxies but counted fewer than 60. If you placed our Milky Way at its center, the nearest major galaxy would be so distant, human civilization might have risen and fallen before its light reached us. What creates these eerie blank spots? The leading theory points to the universe's infancy, when tiny quantum fluctuations snowballed into density variations during inflation. Regions with slightly less matter expanded faster, stretching into voids, while denser areas collapsed into galaxy clusters. It's like rolling dough with uneven raisins, some clumped together, leaving empty stretches between. But here's the twist: these voids aren't completely empty. They're threaded with dark matter's invisible scaffolding and faint traces of hydrogen gas so sparse, a single cubic meter might hold just one atom. Some even harbor void galaxies, lonely outposts that drifted into the emptiness, their starlight stretched redder by the void's gravitational pull. These isolated galaxies evolved differently, with fewer cosmic collisions to trigger star formation, offering a glimpse of how the universe might look if structure had never taken hold. The real mystery is what these voids mean for the cosmos's limits. Could they be evidence of a larger, unseen structure, cosmic cracks where the fabric of reality thins? Or portals to other domains, like bubbles in a multiverse foam? Maps of the Laniakea supercluster reveal voids as defining features, not accidents. They shape the universe's architecture as much as galaxies do, carving out the negative space that gives the cosmic web its form. So when we search for the universe's edge, we might be looking in the wrong places. The answer could lie not in the glittering galaxies, but in the silent voids between them, where the absence of everything speaks volumes. Bubble universes aren't just science fiction, they might be the hidden architecture of reality itself. Picture a pot of boiling water with bubbles constantly forming, growing, and popping. Now scale that up to cosmic proportions. According to eternal inflation theory, our universe could be one tiny bubble in an endless, frothing multiverse, each bubble expanding with its own unique physics. Some might have stronger gravity, others might harbor extra dimensions, and a few could be so alien that time itself flows differently. But here's the twist: these bubbles don't exist in isolation. They drift, collide, and sometimes even merge, leaving behind cosmic fingerprints we might be able to detect. One of the most tantalizing clues could be hiding in the cosmic microwave background, the afterglow of the Big Bang. If our universe once bumped into another bubble, the energy from that collision would have left an imprint, like a scar etched into the fabric of space-time. Scientists have scoured the CMB for these telltale signs, hunting for unusual temperature patterns or circular anomalies that could betray a long-ago cosmic fender bender. Imagine finding a bruise on an apple, except the apple is the entire observable universe, and the bruise is a relic of a multiversal traffic jam. But what would such a collision mean for the limits of our universe? For starters, it could redefine what we consider the edge. If another bubble universe grazed ours, the boundary between them wouldn't be a wall, it'd be a zone of chaos, where the laws of physics as we know them might warp or even break down. Time could flow differently there, gravity might reverse, or matter could behave in ways that seem impossible by our standards. It's like two soap bubbles touching. Where they meet, the surface tension creates a shimmering, unstable membrane. In cosmic terms, that membrane could be a portal to realms beyond our comprehension. This isn't just theoretical. Some models suggest these collisions could explain mysterious features in the CMB, like the infamous cold spot, a strangely frigid patch of sky that defies standard cosmology. Could it be the ghostly imprint of a neighboring universe brushing against ours? If so, then the so-called edge of our universe isn't a true boundary at all, but a dynamic frontier where realities intersect. The implications are staggering. If bubble universes collide, then the multiverse isn't just a collection of isolated worlds. It's a living, shifting network where the very idea of limits becomes fluid. Our cosmic horizon might not be the final word on size or scale. It could just be the edge of our local bubble, with untold others lurking just beyond. And that changes everything. Instead of asking how big the universe is, we might need to ask how many layers it has and what happens when they touch. At the opposite extreme from cosmic voids and infinite horizons lies the smallest possible division of space, a realm so tiny it makes atoms look like sprawling cities. This is the domain of the Planck length, a distance so small that measuring anything shorter becomes meaningless. To put it in perspective, if you scaled up a single atom to the size of the observable universe, the Planck length would still be smaller than a single grain of sand on Earth. At this incomprehensible scale, the smooth fabric of spacetime we take for granted dissolves into a seething, turbulent foam, a quantum froth where reality itself flickers in and out of existence. This isn't just theoretical speculation. The Planck length represents the point where gravity, normally too weak to notice at atomic scales, becomes as powerful as the other fundamental forces. Here, the warping of spacetime grows so intense that space and time lose their classical meaning, becoming a chaotic dance of virtual particles and microscopic black holes popping in and out of existence. This quantum foam, as physicist John Wheeler called it, suggests that spacetime isn't smooth and continuous like a sheet of glass. It's more like the churning surface of a boiling pot, with bubbles of energy forming and vanishing in fractions of a second. But why does this matter for cosmic limits? because if space-time is granular at this level, then the universe might have a built-in resolution, a pixel size beyond which you can't zoom in further. Just as a digital image breaks apart when magnified too far, reality itself could become blurry and undefined at the Planck scale. This would mean that infinite divisibility, an idea dating back to ancient Greek philosophers, hits a hard stop. You can't divide space into pieces smaller than the Planck length any more than you can divide a pixel into half pixels. The implications ripple outward. If space-time is foamy, then even the vacuum of empty space crackles with energy, a phenomenon detectable in subtle ways. Some theories suggest that high-energy cosmic rays, traveling across billions of light-years, might scatter slightly as they pass through this quantum turbulence, like light shimmering through hot air. Future experiments like ultra-precise quantum gravity probes or observations of distant gamma-ray bursts could one day catch these faint distortions, offering our first glimpse of the universe's underlying graininess. Yet the most mind-bending possibility is that this quantum foam might connect to the largest scales of the cosmos. Just as bubbles in a boiling pot merge and pop, the froth at spacetime's foundation could be linked to the birth of entire universes. Some models propose that new bubbles of spacetime constantly emerge from this foam, each potentially budding off into its own self-contained cosmos, a process that could make our universe just one bubble in an endless, frothing multiverse. So while we search for limits at the edges of the observable universe, the ultimate boundary might lie beneath our feet, or rather, beneath the very fabric of reality itself. The Planck length isn't just a scientific curiosity. It's a reminder that the universe's mysteries aren't only written in the distant stars, but in the chaotic, flickering depths of spacetime's smallest scales. And if we ever learn to read that turbulence, we might uncover truths far stranger than anything we've yet imagined. Dark matter is the universe's silent architect, an invisible hand sculpting the cosmos from the shadows. While stars and galaxies glitter like decorations on a grand cosmic tree, it's the hidden roots of dark matter that give the universe its shape. This mysterious substance doesn't emit, absorb, or reflect light, yet its gravitational pull is so powerful, it bends the very fabric of space, weaving a vast web that stretches across billions of light years. Picture a spider's silk, nearly invisible but strong enough to catch galaxies like dewdrops. Without this unseen scaffolding, the universe as we know it would fly apart, its structure unraveling into chaos. But here's the puzzle. If dark matter is everywhere, why isn't it spread evenly? Instead, it clumps into filaments and halos, creating dense knots where galaxies cluster and vast voids where almost nothing resides. These uneven distributions aren't random, they're relics of the universe's earliest moments, when quantum fluctuations during inflation were amplified into cosmic valleys and mountains. Dark matter settled into these wrinkles first, its gravity drawing in ordinary matter like a magnet pulling iron filings. The result, a universe organized into a colossal network, with galaxies strung along dark matter's threads like pearls on a necklace. Now, the Euclid telescope is on a mission to illuminate this shadowy framework. Launched by the European Space Agency, Euclid's razor-sharp eyes are scanning billions of galaxies, measuring how their light bends as it passes through dark matter's gravitational field, a phenomenon called weak gravitational lensing. By mapping these subtle distortions, Euclid will trace the invisible mass-warping spacetime, revealing the hidden blueprint of the cosmos. But the real prize lies in the anomalies. If dark matter's distribution shows unexpected patterns, strange edges, abrupt drops, or unexplained symmetries, it could hint at something even more profound, boundaries we never knew existed. Could these irregularities be fractures in the cosmic egg, evidence of a multiverse bumping against our own? Or might they mark the limits of dark matter's influence, where its grip weakens and another force takes over? The answers could redefine not just what we know about the universe's structure, but its very nature. Dark matter isn't just holding galaxies together, it's holding up a mirror to reality itself, showing us a reflection we're only beginning to understand. The Kardashev scale flips our entire perspective on cosmic limits because for civilizations far beyond our own, boundaries aren't obstacles to overcome, but raw materials to reshape. Picture a Type 3 civilization, one capable of harvesting the energy output of an entire galaxy. While we strain to glimpse the edge of the observable universe, such a society might see space not as a fixed stage, but as a construction zone. To them, the universe's limits could be mere design challenges, solved by engineering feats that bend the laws of physics as we know them. Take Dyson spheres, hypothetical megastructures that encapsulate stars to capture their energy. For a Type 2 civilization, building one would be like erecting a hydroelectric dam on a cosmic river. But scale that ambition up to a Type 3 society, and entire galaxies could be rewired into vast energy grids. Imagine networks of black holes harnessed as power plants, their accretion disks funneled into quantum reactors, or dark matter filaments tapped like galactic-scale power lines. These aren't just sci-fi dreams, they're logical extensions of physics we already understand, pushed to staggering extremes, and that's where the Kardashev scale gets truly mind-bending. A civilization advanced enough to manipulate spacetime itself might treat cosmic horizons like we treat ocean's barriers that once confined us, until technology turned them into highways. Wormholes could become transit routes, folded dimensions might serve as shortcuts, and the heat death of the universe, just an engineering problem to solve, perhaps by siphoning energy from other brains in the multiverse. Yet here's the humbling twist. Even a Type 3 civilization would face fundamental limits. The speed of light, the holographic principle, quantum uncertainty, these aren't just hurdles but cosmic guardrails. No matter how advanced, all beings might share the same existential questions. Is the universe infinite or just unimaginably large? Are we alone, or is the cosmos teeming with others who have already reshaped it beyond recognition? Kardashev's scale doesn't just measure energy use, it measures how deeply a civilization can read the universe's blueprints and how boldly it can redraw them. So where does that leave us, staring up at the night sky, wondering if those flickering stars are already someone else's power plants, their light the exhaust of technologies we can't yet fathom? The universe's limits might not be fixed, just waiting for the right minds to redefine them. The universe doesn't just feel fine-tuned for life, it is fine-tuned down to the most delicate decimal places. Take gravity, for instance. If it were even slightly stronger, stars would burn too hot and fast, collapsing into black holes before life could emerge. Too weak, and matter would never clump into galaxies at all. Cosmologist Martin Rees called this the just right principle, a cosmic Goldilocks scenario where the fundamental constants align with eerie precision to make life possible. But here's the unsettling question. Is this perfection an accident or evidence of something deeper? The Anthropic Principle suggests an answer. In its simplest form, it states that the universe must accommodate observers like us, because if it didn't, we wouldn't be here to question it. Think of it like a lottery winner marveling at their odds. Someone had to win, and their existence doesn't prove the game was rigged. But when applied to cosmology, this idea takes on profound weight. The strength of nuclear forces, the mass of electrons, even the vacuum energy of empty space, all seem calibrated within razor-thin margins to allow atoms, chemistry, and ultimately life. Tweak any one of them, and the universe becomes either a sterile void or a chaotic mess. Some theorists take this further, proposing that these just right conditions hint at a multiverse, a vast ensemble of universes, each with different physical constants. In most, the numbers don't add up and life never arises, but in a rare few, like ours, the dice land perfectly. It's like walking into a tailor's shop and finding a suit that fits you flawlessly, not because it was made for you, but because there were millions of ill-fitting suits you never saw. Yet the Anthropic Principle has its critics. To some, it feels like a cop-out, a way to sidestep the deeper mystery of why these constants are what they are. Why should life's existence dictate the laws of physics rather than the other way around? And if the universe is fine-tuned, who or what did the tuning? The answers might lie beyond pure physics, in realms where science brushes against philosophy. What's clear is this: the universe's limits aren't arbitrary. They're boundaries shaped by the very conditions that allow us to ponder them. In a cosmos where gravity was weaker, dark energy stronger, or matter less stable, the question of cosmic limits might not even arise because there'd be no one left to ask. What if the universe isn't a one-time event, but a never-ending cycle, an infinite loop of birth, death, and rebirth? This is the radical vision of cyclic cosmology, a theory that trades the traditional linear timeline for something far more profound, an eternal cosmic heartbeat. Imagine the universe not with a definitive beginning or end, but as a phoenix perpetually rising from its own ashes. Every collapse leads to a new Big Bang. Every ending births another beginning, in a rhythm stretching across time with no start and no finish. At the forefront of this idea is Roger Penrose's conformal cyclic cosmology, a theory as elegant as it is mind-bending. Penrose proposes that when our universe reaches its final state, a cold, empty expanse where even black holes have evaporated, something extraordinary happens. All particles lose their mass, distances become meaningless, and the universe resets into a state mathematically identical to the primordial singularity of the Big Bang. It's not just a new universe emerging from the old. It's a seamless continuation where the end of one cycle becomes the indistinguishable beginning of the next. Think of it like turning a vinyl record into a CD. The analog grooves of the old format filled with scratches and where are translated into pristine digital code, erasing imperfections while preserving the essence of the music. In Penrose's model, the universe undergoes a similar transformation at the end of time, shedding its worn-out structure to emerge fresh and reborn. The most astonishing evidence: Penrose and his team claim to have found faint circular patterns in the cosmic microwave background, possible imprints of collisions between black holes from a previous cycle, like cosmic echoes reverberating through eternity. But cyclic cosmology isn't the only take on eternal rebirth. The Big Bounce theory suggests that instead of a cold reset, the universe collapses under gravity's pull until quantum effects trigger a rebound, a cosmic trampoline where contraction flips into expansion. Here, the universe doesn't fade away. It contracts to an unfathomable density before exploding outward again, carrying remnants of its past into each new iteration. The implications are staggering. If the universe cycles endlessly, then time itself becomes a spiral, not an arrow. There's no final limit, no ultimate boundary, just an infinite dance of creation and destruction. Each cycle might tweak the laws of physics slightly, producing universes where gravity is stronger, dark energy weaker, or matter arranged in ways we can't yet imagine. Yet for all its grandeur, cyclic cosmology raises haunting questions. If the universe has no true beginning, does the concept of a first cause even make sense? Could information, the building blocks of reality, survive from one cycle to the next? or is each rebirth a total reset? And if we're living in just one iteration of an infinite series, how many versions of us have come before and how many will follow? The answers might lie in the fabric of space-time itself. If Penrose's circles are confirmed, they'd be the first tangible evidence that our universe is just one chapter in an endless story. Until then, cyclic cosmology remains a breathtaking reminder that the cosmos's greatest limits might not be walls, but turning points, moments where endings and beginnings blur into one. Quantum entanglement is the universe's ultimate magic trick, a phenomenon so bizarre, even Einstein called it spooky action at a distance. Picture two particles born from the same quantum event, forever linked no matter how far apart they drift. Change the spin of one and the other instantly flips to match, as if they're dancing to some hidden rhythm across the cosmos. This isn't just theoretical. It's been confirmed in labs worldwide, with particles separated by hundreds of miles responding to each other faster than light could travel between them. At first glance, this seems to shatter the cosmic speed limit set by Einstein's relativity, which states nothing can outpace light. But here's the twist: entanglement doesn't involve any actual signal or energy zipping through space. Instead, it's as if the particles share a single quantum identity, their fates intertwined in a way that transcends distance. Think of it like a pair of gloves. If you find one glove is left-handed, you instantly know its partner is right-handed, no matter where it's hidden. The information isn't traveling, it's just part of a deeper, pre-existing connection. The real breakthrough came with experiments like the ones by Elaine Aspect in the 1980s, which closed loopholes that skeptics had raised. By measuring entangled photons in ways that ruled out any hidden variables or secret communications, Aspect's team proved that quantum non-locality, this eerie, instantaneous link, was real. Later, teams in Vienna and China stretched the distances further, beaming entangled particles over fiber optic cables and even via satellite, with the results holding firm. In 2017, China's Misha satellite sent entangled photons to ground stations separated by over 700 miles, and their quantum bond stayed unbroken, defying classical intuition. Yet the most tantalizing question remains: could this spookiness hint at something deeper about the universe's fabric? Some theorists suggest entanglement might weave space-time itself together, with every particle's connection stitching the cosmos into a vast, interconnected web. Others propose it could be a doorway to higher dimensions, where particles communicate through unseen layers of reality. And if that's true, then the speed of light might not be the ultimate limit, just the limit of our current understanding. For now, entanglement remains both a cornerstone of quantum mechanics and one of its greatest mysteries. It doesn't break the universe's rules, it reveals rules we never knew existed. And as we push these experiments further, from lab benches to orbiting satellites, we're not just testing physics, we're probing the very nature of connection in a universe far stranger than we imagined. Our brains were never designed to comprehend the true scale of the cosmos. They evolved to navigate a world of trees, rivers, and predators, not galactic superclusters and cosmic voids. This mismatch between our biological wiring and the universe's grandeur creates a perceptual funhouse where reality bends in ways we can't intuitively grasp. Take something as simple as the moon illusion. When the moon hangs near the horizon, it appears enormous, yet high in the sky, it shrinks to a mere coin. The moon hasn't changed size. Our brain's depth perception tricks us, compressing the sky into a flattened dome and distorting objects within it. This same cognitive quirk makes cosmic distances feel meaningless. We can recite that the Milky Way spans 100,000 light-years, but that number carries no visceral weight. To truly feel it, imagine shrinking our solar system to the size of a cookie. On that scale, the nearest star would be another cookie over 4 football fields away, and the Milky Way would stretch wider than the continental United States. Even then, our brains struggle to map such emptiness. The universe isn't just vast, it's inhumanly vast, operating on scales that defy the very tools evolution gave us to measure our surroundings. Optical illusions reveal how easily perception fails. The shepherd's table's illusion shows 2 tabletops of identical dimensions that appear radically different, one wide and squat, the other tall and narrow, simply because our brains prioritize context over raw data. Similarly, when we look at a galaxy, we instinctively frame it as an object within our visual field, not a structure millions of times larger than anything our ancestors ever encountered. This automatic scaling down warps our understanding, making the cosmos feel like a model we can hold in our hands rather than an expanse we're embedded within. Even time eludes our grasp. We measure cosmic events in billions of years, yet human history spans a mere eye blink in comparison. Try picturing the age of the Earth as a single calendar year. Dinosaurs wouldn't appear until mid-December, and all of recorded history would occupy the last 14 seconds of New Year's Eve. Our minds aren't built to process durations where mountains rise and erode like ocean waves, or where stars live and die in spans that dwarf every human effort. So when we ask whether the universe has limits, we must also ask, are those limits real, or are they imposed by the constraints of our perception? The cosmos might be infinite, but our ability to conceive infinity is fundamentally bounded by the meat and electricity of a 3-pound brain. Perhaps the greatest cosmic frontier isn't out among the stars, it's inside us, waiting for the day when our understanding catches up to the universe's grandeur. The next generation of telescopes won't just peer deeper into the cosmos, they'll rewrite its atlas entirely. Take the James Webb Space Telescope, already revolutionizing our view with its infrared eyes. While Hubble showed us stunning galaxies, Webb pierces through cosmic dust like an X-ray, revealing the universe's nursery rooms where stars are born. But the real game changer lies in its ability to analyze the atmospheres of exoplanets. Imagine detecting water vapor or even potential biosignatures on worlds light years away, not as blurry dots but as dynamic environments. Webb's observations of TRAPPIST-1 planetary system could one day answer whether we're alone in the universe, turning abstract speculation into tangible data. Then there's the Vera-C, Rubin Observatory's Legacy Survey of Space and Time, or LSST, a project so ambitious it'll catalog more galaxies in a single night than most telescopes do in years. With a lens wider than a giraffe is tall, LSST will scan the entire southern sky every few nights, creating a cosmic time-lapse movie. This isn't just about counting stars, it's about catching the universe in action. Supernova flaring, asteroids tumbling, even the subtle warp of space-time around invisible dark matter clumps. LSST could uncover interstellar visitors like Oumuamua on a regular basis, or spot gravitational lenses bending light from galaxies we'd otherwise never see. But the future doesn't stop there. The European Space Agency's Euclid mission is mapping dark matter's shadowy web across billions of light years, while NASA's Nancy Grace Roman Space Telescope will hunt for rogue planets, worlds untethered to any star, drifting through the galactic void. These instruments aren't upgrades, they're paradigm shifts. Together, they'll transform static sky charts into dynamic, 3D models where dark matter's scaffolding is as visible as the galaxies it cradles. The most thrilling possibility: these telescopes might stumble upon anomalies that defy current physics, ancient stars older than the universe itself, patterns in galaxy distributions that hint at a multiverse, or even artifacts of alien engineering. Every time humanity builds a better window to the cosmos, we discover how much we've been missing. The universe's next chapter isn't just waiting to be read, it's waiting to surprise us. But what if the universe's boundaries aren't just physical barriers, but limits of human understanding itself? This is where cosmology collides with philosophy, where telescopes give way to pure thought experiments. Immanuel Kant, the 18th century philosopher, wrestled with this dilemma through his concept of antinomies, pairs of equally logical but contradictory conclusions about reality. His first antinomy presents two seemingly irrefutable arguments: that the universe must have a beginning in time and space, and simultaneously that it cannot have one. Try proving the universe is finite, and you'll hit the inevitable question, what lies beyond. Yet argue for infinity, and your mind staggers under the weight of endlessness. Kant's brilliance was realizing both arguments feel equally valid because space and time aren't absolute properties of the universe. They're the very lenses through which we perceive it. Think of it like a fish trying to comprehend the shore. The water defines its entire reality. The concept of dry land might be mathematically describable but experientially unimaginable. Similarly, our brains evolved to navigate a world of medium-sized objects moving at modest speeds, not the warped space-time of general relativity or the quantum froth at reality's foundations. When we push questions about cosmic limits to extremes, we're not just probing the universe, we're testing the boundaries of our own cognition. The discomfort we feel when contemplating infinity or the universe's edge isn't necessarily about the cosmos itself, but about hitting the walls of our mental aquarium. This philosophical framing transforms how we interpret modern cosmology. The Big Bang's singularity, the holographic principle's information paradoxes, even dark energy's accelerating expansion. These aren't just physics problems. They're mirrors reflecting the limits of human reason. When physicists speak of the Planck length or the cosmological horizon, they're not just marking distances, they're sketching the edges of where mathematics can take us before our intuition fails completely. The universe might not have an edge in any traditional sense. Instead, what we're calling limits could be the points where our current frameworks crumble, where new paradigms must emerge to make sense of the data. Existentially, this realization is both humbling and electrifying. If the cosmos' true nature lies beyond our perceptual and cognitive limits, then every scientific breakthrough is less about discovering absolute truths and more about expanding the territory we can meaningfully explore. Like prisoners in Plato's cave mistaking shadows for reality, we might be interpreting cosmic mysteries through the only vocabulary we have, one shaped by the very constraints we're trying to transcend. The most profound boundary in the universe may not be written in the stars, but in the architecture of the human mind itself. Humanity stands at a crossroads not just of technology, but of conscience. As we reach for the stars, we're forced to ask, is crossing cosmic boundaries our birthright, or are we playing with forces beyond our wisdom? The dream of interstellar travel ignites our imagination, but it's shadowed by risks we've barely begun to reckon with. Picture a spacecraft venturing to Proxima Centauri, our nearest stellar neighbor. Even at a fraction of light speed, a collision with interstellar dust could unleash energy comparable to a nuclear blast, turning the vessel into a high-speed projectile, endangering anything in its path. And what if we're not alone? The same ambition that drove explorers to cross oceans could, in space, become an invasive force, carrying Earth's microbes to alien ecosystems or disrupting civilizations we don't yet understand. Planetary protection protocols exist for this very reason. NASA and other agencies treat celestial bodies like archaeological sites, sterilizing probes and restricting landing zones to preserve their pristine states. Europa's subsurface ocean or Mars' ancient riverbeds might hold fragile biosignatures, clues to life's origins that a single Earth bacterium could obliterate. Yet these safeguards clash with commercial interests eager to mine asteroids or colonize Mars. The tension is palpable. Do we prioritize caution, or does progress demand we accept contamination as collateral damage? The ethical dilemma runs deeper than microbiology. Some argue that stagnation poses its own existential threat, that by not pushing boundaries, we risk entombing humanity on a vulnerable planet. A supervolcano, asteroid impact, or our own self-destruction could erase millennia of progress unless we become multiplanetary. Elon Musk frames Mars colonization as a backup drive for civilization, while Carl Sagan warned that staying earthbound ensures our eventual extinction. But others counter that space expansion could replicate Earth's worst patterns: resource exploitation, territorial conflict, even the suffering of generations born in artificial habitats far from home. Perhaps the most haunting question isn't whether we can overcome cosmic limits, but whether we should. Indigenous philosophies like the Maori concept of Kaishiakatanga, guardianship, remind us that exploration without reverence leads to ruin. What if the universe isn't a frontier to conquer, but a sacred equilibrium we're meant to join? The answer lies not in stopping, but in stepping forward with humility, recognizing that every boundary we cross must be matched by wisdom we've earned. From the infinite stretch of bubble universes to the flickering quantum foam at spacetime's smallest scales, the search for the universe's limits has taken us to the edge of imagination and left us staring into the unknown. We've traced the contours of cosmic horizons, wrestled with dark energies accelerating push, and dared to ask whether reality itself might be a simulation running on some unfathomable hard drive. Yet for all the theories, multiverses stacked like pages in a book, cyclical universes reborn from their own ashes, or hidden dimensions curled tighter than a clenched fist, one truth remains: the beauty lies not in the answers but in the pursuit. Every telescope pointed skyward, every equation scribbled on a chalkboard, every late-night debate under the stars is a testament to humanity's restless curiosity, our refusal to accept "we don't know" as a final answer. Carl Sagan's words in pale blue dot echo louder now than ever. That's here, that's home, that's us. Against the backdrop of a cosmos so vast it numbs the mind, our tiny, shimmering planet is the only place we know for certain harbors life. And yet, from this speck of dust, we've decoded the life cycles of stars, uncovered the fingerprints of the Big Bang, and sent whispers of our existence hurtling into the void. The universe may be indifferent to our questions, but in asking them, we've woven something extraordinary, a story of wonder that spans generations. So as we stand at the threshold of the unknown, let's not forget to marvel at how far we've come. Whether you're drawn to the elegant math of string theory, the haunting silence of the Fermi Paradox, or the mind-bending possibilities of the Holographic Principle, remember the cosmos isn't just out there. It's in us. Every time we look up and wonder, we're touching the edge of something infinite. Now it's your turn. Which cosmic limit theory sparks your imagination? Drop your favorite in the comments below, and if you've enjoyed this journey through the universe's greatest mysteries, don't forget to subscribe. The cosmos has plenty more secrets to share, and we're just getting started.